Hello everybody, welcome to the webinar summarizing our scientific research on coupled wind and fire interaction. Warm welcome to the small groups of representatives at ITB headquarters, and warm welcome to everyone joining us online. Also, if you're watching this a little bit later than today, I'm happy that you've reached out to this material. I hope it proves to be valuable for years. For me, this is quite a special event because this truly is my first real scientific project that I have ever had chance to coordinate as a principal investigator. The first one that I've written and won, certainly a milestone for a career of a researcher. The project we're talking about is a scheme in the National Science Center of Poland, NCN. The project is called Opus, and the title is Wind Effects on Building Fires in a Multiparametric Risk Assessment with Numerical Modeling. Before we go into details of what has been done, let me briefly give you the context of why we are even working on the wind and fire interaction at ITB. So around 2015-ish, we have done a very big case study in central Warsaw of a historical shopping mall in which you could only use natural smoke exhaust ventilators to extract the smoke from. And this damn building was really difficult. You really could not get a good working system unless you made it work together with the wind, due to how the building was shaped. And for us, it was a very steep jump into wind engineering, because we suddenly had to add wind engineering into fire engineering to resolve the issues on that building. Thankfully, at that time, we had very good wind engineers in ITB. We had Professor Żurański, who was the godfather of Polish wind engineering, working in this office. And we were capable of catching up very quickly and adapting the wind engineering to the needs of our commercial project on smoke control. At that point, I did not realize at all that this is something not normal. And we figured it out a few years later, talking with other people who seem to have similar struggle as we did on wind modeling, that it's actually not such a simple thing. And then we started thinking, okay, we have figured out some clever schemes, some interesting approaches how to combine wind and fire. We wrote a big papers for fire technology, wind and fire coupled modeling. And since then, we've been working on developing this further and further and further. In 2020, I have submitted this project as my attempt to have a really good holistic understanding of the impact of wind on a building fire. And yeah, we got it. It's been 3 years since the moment we've started. We're about to approach the final days of the project. And here we are, finally capable of telling you the assumptions we had, the pathway we went, the models that were developed, and how everything connected together in the final assessment that I'm going to share with you at the end of this webinar. You will see 5 presentations, this introduction, and I will also summarize the webinar. You will also meet the project team, Bartosz Miechówka, who did analysis on the design fires and some fundamental fire-related assumptions for the project. Dr. Grzegorz Krajewski, who did evacuation modeling and helped me assess the outcomes of the project, and Dr. Paulina Jamińska, who was the postdoc in this project and who carried most of the numerical work presented in here. So yeah, that's the brief historical overview of how we ended up in this room today. Let's try and talk about wind now. I've started my project with this quote from a children's song telling the story of Great Fire of London. As the wind it blew, the sparks they flew, and the flames they started leaping. I found it beautiful that almost 400 years ago, the profound impact of wind on fires was already recognized to a level it became a part of the culture. And I think that's the fact. It is kind of obvious that wind and fire are things that when they are together, the outcomes are completely different than when there is fire with no wind at all. And we knew it intuitively that the fire changes when it's subject to wind. We know that the consequences of the fire will be different in wind conditions. The big question is how much, when, how, and these are the ones that we're trying to assess. When I was looking, preparing my papers on wind and fire, I came across an FPA report that summarized incidents in which there were fatalities in. And in that report, I found a quote that 60% of all of the incidents perhaps could have had wind as a force that led to the outcomes of the fire. 60%, that's tremendous. In 30 of those fires, the wind impact has been confirmed. It's obvious that it was the wind, the thing that made this fire so much better. For 10% of the cases, it was quite probable, however, not undocumented. So even looking at the outcomes of the fires from the statistics, we see that fires in wind conditions can be severely more dangerous. I also have in mind summer, I think it was 2021, a very warm summer in UK, where there was this worst day for London Fire Brigade for ages, where they had the biggest number of fire incidents happening in one day. An outcome of a very dry period and unfortunate weather patterns led to the most challenging day for firefighters. I've checked the statistics on that day, and the wind on that day was not very strong. It was actually way below the median wind for London area, which from my perspective means that London won a coin toss. If the coin landed on the other side, perhaps the outcomes of that day would be different. It's paramount for us that we study wind, and we understand it as wind engineers. Without that, much of our assessment is invalid. And I also find wind a really funny and interesting phenomenon. It's simply mesmerizing sometimes. Here's a funny picture from one of our large-scale experiments carried by Dr. Paweł Sulik from ITB some years ago. What you see on the picture is a two-story building, fully flash-over fire in that building. That was a really large fire, like 10 megawatts plus, like seriously large fire. And that day we had quite strong wind, and the plume is horizontal. The thermal plume from such a big fire has been totally dominated by this wind. And it was not even a very strong wind. I think it was like 7 meters per second. So it was not really hurricane strength. And it just shows how significantly and easily the wind can change the outcomes of the fire, in this case, the thermal buoyancy of the plume, which obviously should be vertical, not horizontal. So I see it as an important phenomenon, and I find a lot of joy in studying it. When you think about building fires, the wind can interact with the building on its envelope, especially at the inlets and outlets of the building, the points where the building meets the environment, the atmosphere. This is where the wind can act as a source of force through pressures. It can create very difficult to predict pressure patterns around. It can create pressure gradients between walls or roofs of the building. It can cause a very strong updraft force on the roof, which means the wind is sucking the roof up with a force of even hundreds of or thousands of pascals. Finally, it can significantly alter the flows inside the compartment, changing how the physics inside work, where the thermal smoke plume goes, how the smoke layers are spreading in the compartment. Everything that is important for assessment of smoke and heat extraction systems performance can be influenced by wind, to be honest. And outside of the building, many other phenomena happen. We don't only care about removing the smoke from our buildings, we start to care about where the smoke goes when we extract it. And for this reason, wind is obviously the major force driving the transport of the smoke in an urban environment. It can push smoke against buildings, it can protect buildings from smoke, it can help smoke plumes go far up into the atmosphere, it can push the smoke plumes down to the ground level where people are. It can change the direction, surprising those who are in upwind direction. So certainly a phenomenon that significantly impacts what happens outside of the fire. Now, performing a scientific analysis of wind and fire modeling, I'm inspired by a graph by Professor Schlunzen. She has made a graph that shows different scales of phenomenon in the scale of time and size of those phenomenon, going from turbulence that happens instantaneously in the tiniest vortices down to colomograph scale, up to global circulation, meaning the weather patterns, El Nino and such. And there is a plethora of different atmospheric phenomena happening between those. Inspired by this plot, I've tried to make a one for fire following the similar fashion, and I've put the phenomena that I find relevant to fires in here, placing building fires in the middle of the graph. Scales from 1 to hundreds of meters, time from minutes to perhaps dozens of hours. This is the physical and time scales that we operate when working with fires in built environment. Now, this is pretty much the area where we operate as fire safety engineers. We don't go below, we don't really go above. Of course, we do include some phenomenon like turbulent combustion or ignition in our engineering assessment, but it's not through direct explicit modeling, but rather introduction of submodels and routines that help us introduce those conditions into analysis that we perform. The same happens for larger phenomena, atmospheric boundary layer, stuff that in terms of wind happens at the scale of kilometers in the upper parts of the atmosphere. They impact the bottom layer where the buildings are. We don't model that directly. It's pointless to model that directly in our CFDs. We have to find models that will allow us to put that into. So here you can see a first challenge that emerges when one tries to merge wind engineering and fire science. They simply act at different scales. And you have to find the place where those scales are the same, in which you carry your analysis. And for everything happening at a different scale, you have to figure out how to model that to get a reasonable outcome. And boy, that was a significant part of this project, which you will hear about in the next presentations. So now let's try to summarize where we are. I will say we are capable of modeling wind, we are capable of modeling fire. That perhaps is a bit far statement, and I guess many scientists would disagree that we are capable of modeling fire, but I think for engineering requirements, fire modeling is something that we commonly perform, and it's nothing unexpected to do. It's just our bread and butter. That's our engineering analysis. At least in Poland, we did like this. In 2017-18, when we've published the papers in fire technology, we've claimed that we know how to model wind and fire as a coupled analysis. We've shown how does one perform such an analysis, which things are meaningful for that analysis, how does one come to the boundary conditions, initial conditions, how does one define the problem, and how does one solve it. So I would say the coupled wind and fire modeling is also known. Having this framework available, we were capable already in the past predicting outcomes of a single design scenarios in buildings in the case of wind. And we were able to also assess the general influence of wind on smoke control systems, some stuff that we have also published previously. Last one was on the SFP Europe last year, where we've talked about shifting the aerodynamic discharge coefficient paradigm. Anyway, we are very well capable of that, and we are doing that in our everyday engineering. So why do we need a scientific project? Why do we need all this hassle? Because we want to introduce a multiparametric analysis. We want to go beyond. We don't want to understand the outcomes of a single scenario. I want a distribution of scenarios. I want to understand holistically how wind affects my fire, and can I generalize this thinking for better outcomes for engineering and science. That is the point of setting up a research grant in the National Science Center and doing that for 3 years. Now, if we go a little deeper into that, where the challenge is, fire engineers, we like to simplify fires. We love the fire phases, growth, flashover, decay phase. We love to simplify fires. I often say that the fire science is science of complexity and simplifying those complexities so we can use them in practice. But this is simply a description of a fire that has happened, or a fire that may have never happened. It's just a single course of a fire. I like to view it as a more complicated phenomenon, something that begins, ignites, then perhaps spreads, grows, And based on how the course of the fire went, it creates damage or loss. It's not a single line on a plot, it's thousands of possible plots that you could have. Now, if you think about it, you put systems and wind into that equation, you end up with a significantly more complicated image. Your systems in the building will affect the fire itself, the way how it spreads, and how much damage it does. And wind will affect all of those above. It will affect the systems, it will affect the growth. It will also perhaps drive or prevent damage. So even though the graph is simple, it's a complicated mesh of interactions between those things, very nonlinear. But to make it worse, you cannot simply multiply fires by systems by wind. These are complicated phenomena. In terms of fires, I like to think about fire as a collection of events that happen one after another. The fire has to ignite, then if it has the capability to spread to other objects, it will. If it doesn't, it will decay. If it has enough ventilation, it will be driven by oxygen. If it doesn't have it, will be driven by fuel. It's a bunch of events that happen consequently one after another, very difficult to predict when they will happen. And some people try to present this as a fault tree analysis. I don't really like this method because it gives you false thinking that you can predict fires. You cannot. It's very difficult. I like to think about it as a collection of things that happen in progression. If you think about safety systems you can probably reduce to probability distributions. You can put a number on probability that a particular system will work in case of a fire. My student Bartosz, who done this analysis, has put a note that every single data source he found for this was older than him. A very difficult statement to work with, but that's the reality. It's very hard to get reliable data, and just a very few sources that would give you, let's say, the new results in here. But yeah, we can simplify systems into some sort of probabilities, and it's also conditional probabilities. If my fire alarm doesn't work, then my smoke control will not work at all because it doesn't know that there's fire. So yeah, we can sort it out. There's also the element of chaos, the humans, which is very difficult to prescribe and will behave very different from what we usually assume. A psychological thing that most of the evacuation time will be defined in the pre-evacuation phase, for example. That's very difficult to engineer for. So you have this complicated array, and then you have wind. Wind is something that constantly changes. Wind now, it will be different than wind in 1 hour from now. It's challenging to predict the wind. Of course, we can do it. It's meteorology. Predicting wind in a few hundred years ago in UK was a crime punished by death. Hopefully today it's just a science and modeling. We can predict it, though it's difficult to predict what will be the wind on the day when the fire will happen, because I don't have any idea when the fire will happen. So we can narrow wind into probability distribution. We can figure out from what direction and at what velocity the wind has blown and present it as an outcome for perhaps a whole year of calendar. What is the possible wind directions and velocities? However, when you start to interpret them, some of those velocities may be good for your system, some might be neutral, some may be bad. If the bad ones are the ones that are not very commonly present in your area, you have a good time, but it can be completely obvious. It may be the most common winds that cause the most challenging outcomes of your fires. So you have to be very well aware of these consequences, and this is something we try to map in this project. How to do it? We try to couple all those things, the event trees that represent the fires, the probabilities related to systems and people, and the probabilities related to the wind distribution in one large package that tries to answer the large questions. What will be the effects of wind action for a large group of diverse assumptions? What will it be? It's a very simple question, but you will not find an answer in the literature. There was no projects that would analyze hundreds of winds and fires and tell you that they end up in this distribution. Because we're engineers, not just scientists, we always look to simplifying those things to make them into useful tools for us. So that was another important part of the project, to narrow them down to something that we could use and hopefully share with you today and in the future. We want to find ways how to evaluate the results of those analyses, because we found that there are significant shortcomings in the methods of assessment that we normally use for CFD analysis that perhaps need to be modified if we want to analyze those multiparametric analysis of wind and fires that go into hundreds of scenarios. We wanted to figure out if we can determine the fire and wind risk. So a risk can be the basis of how we design buildings. And I think we found a way that you can actually do it quite well. And there was this one question I had in the back of my head all the time. Is there a safe wind? Is there a wind velocity that I can just ignore, that I don't care about? In some parts of literature, you can find values like 2 meters per second, 3, 5 meters, whatever. But is there a value that, okay, if my wind is lower than that, I can just not touch it at all? It's a question we didn't really find an answer for, but at least I'll give you some hints on how does it look like. And in the course of this presentation, of those presentations today, you will see how we built up our project altogether. We've studied an open car park. I actually have one with me here today. It's a 3D model that we've printed out. We actually printed out the whole part of the city to study it. That's the case study that we've chose to do in this project. We also investigated the small warehouse. You'll learn about the inputs, how we define the boundary and initial conditions for our simulations. You'll learn how we have performed the CFD analysis in this project. And then at the end, I will give you the outcomes. How did we proceed with investigating the results? How did we form conclusions, what those conclusions are, and what can we do with it in the future? So yeah, not everything will be covered in the webinar, because it would have to be significantly longer if you wanted to carry everything, and I'm already taking 2 hours of your precious time. So we've narrowed it down to the most interesting bits. It's still a lot of stuff. We have just finished the seminar in Polish, and we went 5 minutes over the time, so it seems the package is well crafted for those 2 hours. Anyway, that's it for my introduction, and now I will pass to my student Bartosz. Come, Bartosz. Bartosz has joined the project in the first year when we were driving it, and I told him, Bartosz, I have a very simple mission for you. You have to read everything that there's written about the reliability of systems, and you have to analyze every single fire experiment on vehicles in existence. He agreed. He had no idea what he's going into, but actually he did quite well. He's now working at ITB full-time, and we continue working on the boundary conditions, the initial conditions for car park fire simulations. We're working on the design fires of vehicles and the fire sizes in general. So yeah, Bartosz, please explain what you have done in the project. Thank you.
Hello everyone. As Wojciech said before, I joined the project as a student of the then master studies. Now I graduated. I have wrote my thesis about the coupled wind and fire scenarios based on the project that we did. And today I will present to you why we went with the open car park as a case study of ours. The first thing that is very, very good about it, well, not really good, but what is really motivational is that it is very, very burdensome in recent years. There is a lot of car park fires happening. They are happening every year, and they are having a huge they are making huge losses in case of cars, of buildings, and we are not really taking our lessons from one that happened in back and changing the things how we are doing them. And also the open car parks are only ventilated with a passive system, with a natural ventilation that is fully driven by a wind. And for example, if there is no wind, there is no ventilation. And if the wind isn't blowing perpendicular to the open walls of the open car park, there is also no ventilation, because there is no way that the air can actually get into the car park and take the smoke out with it. And talking about the burdensome of those fires, here I have prepared some examples for you. For example, there is a 2017 fire in England. The King's Dock car park have burned down, and it took 1,150 cars with it. The year after it, in New York, King's Plaza Shopping Center car park also burned down, took 120 cars with it. Also, a year later, the Douglas Shopping Center in Ireland also burned, and the 60 cars burned with it. Then another year later, we have the Stavanger airport car park with 300 cars burned, and the building basically collapsed on its own. So as you can see, they are happening every year. And now, last autumn, we have the Luton Airport car park fire in England. That was the biggest car park fire ever, with 1,500 cars burned, and the building basically being unusable. And we in Poland also have a lot of open car parks. For example, here we have the car parks that I built next to the metro stations, so people can take their cars, park them, and then go to a metro and travel the city this way. And there is a lot of these car parks in Warsaw, and I will talk about them later. But now I want to tell you something about the requirements for the natural ventilation of these open car parks. In Poland, we have regulations that is saying that the surface area of the vents must be at least 35% of the surface area of the wall on each level, and that the distance between the walls with the openings must be maximum of 100 meters. So, for example, if we take a car park that is 50 by 20 meters, so its circus is 140 meters, and we take that the height of the car park is 2.7 meters, we came up with a wall area of 378 meters squared. Now we are taking the 35% of this, and we get 133 meters squared of required surface area of the ventilation openings. So we can spread them evenly, so we get 66.5 meters squared of the vent openings on each wall. And as long as we don't make the walls be like 100 meters away of each other, then it's good. And we have achieved the regulations that we need to pass. And the second most second most known regulations are from the approved document B from the UK. And they are quite different because they are not talking about the wall surface area, they are talking about the surface area of the level itself. So we have to provide the vent opening area equal or bigger than 5% of the level floor area. And we need to provide at least 1.25% of the floor surface area on each two opposing walls spread equally. So we can take now two different routes with these requirements. The first one is that we have the same car park, 50 by 20. So we have 1,000 meters squared car park. 5% of this is 50 meters squared, and we are taking it on two opposing walls, 25 meters each. And we are meeting the requirements. The other way that we can do it is we take 12.5 meters squared on one wall, 12.5 meters squared on the opposing wall. So we have the second criteria met. And now we can add the last 25 meters on the third wall, making that we have more access point of the of the wind actually to the building. So now we have only just one closed wall instead of two closed walls. And now that we know how the natural ventilation of car parks work, we will get to the project itself. And as Wojciech talked earlier, we are working on the risk analysis of these car parks. And when you are talking about risk, you are talking about the probability of an event and the consequences of it. So I will talk you through the probability part of it, and then my colleagues will talk you through the consequences part of our risk analysis. For the probability, to calculate the probability of fire, we need to have some data that we can base it on. So we went for the data about how many cars there was in the years 2017, 2019 in Warsaw. Because we are basing the garage in Warsaw, so we went with the data that we have in Warsaw as well. And we came out that the average of the 3 years was 1,329,000 cars registered in Warsaw. Then we went with the number of fires of the passenger cars that were in Warsaw in those years. And we came up with the average of 319 fires per year, or 0.875 fires per day. With those data, we can calculate how likely it is that a single car will catch a fire. Now, when we take the filling of our park and ride car parks in the Warsaw, there was 16 of them at the time of the project, and we take the average number of parking spots in each of the car park and the data about how filled they were on a certain hours in a day, certain points, like this. We have a data that shows us how filled the car park was at 6, at 10, at 13, and at 20. And we have it in percentages and with the number of cars that were expected to be in the car parks at these hours. We have the separate data for work days, for Saturdays and Sundays and holidays. And when we combine all of it together, the number of cars, number of fires, and number of available spaces and expected number of cars in the spaces, we came up with the probability of fire occurring based on the single vehicle that is entering a car park. So we have the probability per visit, and with the probability of a fire occurring in a car park with current filling state. And with this, we have met the probability part of the risk analysis. Now we will go to the consequences. To have the consequences made by the simulations, we have to think about the fire that we will be simulating. And the first thing that we need to know is how big the fire should be. What will be the fire that will be very good representing how the fires go with the car, how the car fires go. So we collect a lot of data from over 20 reports, different journals and publications. The data were ranging from a year 1991 to year 2022. So we have the new data, we have old data, and we have put them together to make one big database of the basically all car fire tests that there were ever made. In total, we have went over 70 research experiments that were analyzed to gather a data that we will be presenting to you. And from the experiments, we have gathered the data about the type of the propulsion, the vehicle masses, the peak heat release rate, time to peak heat release rate, total heat released, mass loss, and the origin of fire. By the origin of fire, I mean the place that the fire was first set in the experiment. And there is a lot of data that we have collected. So we need to make some kind of organization of the data to be able to analyze it and to be able to make a work with it. So we came up with the idea of grouping it through a mass, through a type of propulsion, and through origin of fire. So we have the small cars that the gross vehicle weight is up to 1,399 kilos. We have the medium cars, we have the big cars, and the very big cars, and they all are ranging in different weight classes. And now we have the type of propulsion. We have the internal combustion engine vehicles, we have the battery electric vehicles, and we have plug-in hybrid vehicles. Plug-in hybrid electric vehicles. And we have the origin of fires. It is under vehicle, cabin, body, and engine compartment. By under vehicle, we mean everything like burners, etc., put under the vehicle that were setting the car on fire. By the cabin, we mean the passenger compartment and everything that was burned inside. Body is everything that was outside of the car, and the engine compartment is everything that was in the engine compartment, like electrical circuit fire, like filters and things like this. And then when we group this data in this way, we could make some correlation between the variables that we have. And we made a separate study about this, and we were really, really shocked when we looked at the last graph that is presented here, that the method with burning the car from under it is really, has a really fast time to peak heat release rate compared to other methods. So probably the method when you are putting like a burner beneath the petrol tank or beneath the electric battery of a vehicle, they can change how the fire is growing and the way that the vehicle is burning. And we want to also deeper into this data and try to make a lot of more information out of it, so we can come up with maybe a better understanding of what is happening during these tests. And another part is that we have to have some heat release rates from for our simulation. So we have grouped the data, and now we have a lot of data in our base, and we went with 5th percentile of the result of the small cars, which is 1.4 megawatts. We have went with 15th percentile of result of the small cars, which is 4 megawatts. We have went with 68th percentile of result for small cars, so we have 4.6 megawatts. We went with 15th percentile of results of medium cars. We have 6 megawatts there. We have with 19th percentile of results for big cars. We have 8 megawatts here. And with the 95th percentile of results for a small car, and we have 8.8 megawatts here. The 4 megawatts and the 8 megawatts mark are also known and are commonly used as the design fires for one vehicle when we talk about the 4 megawatts, and for 2 vehicles when we talk about the 8 megawatts fires. So now that we know the probability and we know how big the fires we want to have in our simulations, we need to put them somewhere in our model. So we have decided that the best location to put the fire will be the 4th floor of the car park, because the floor is most exposed to the wind effect, because it's above the buildings near it, so the wind can easily get to this level. And when we are placing the fire on the parking spot on the level, we have decided that the best position would be to put it in the worst possible place. So we have put it on the spot that is next to the entrance to the stairwell that serves as a primary evacuation route for people, and also a primary access point for firefighters to go and put out the fire. So we now have the probability of fires, we now have the designed fires that we want to use, and we now have this scenario that we want to put them in. And I will leave you with this, and now Dr. Grzegorz Krajewski will tell you about the evacuation from the garage and other elements that we used in the assessment.
Good afternoon. I would like to tell you a few words about the Egress from car parks and other fire outcomes used in risk assessment. Especially, first of all, we have to answer ourselves one question: why we are doing that, and how we are going to make the assessment of our system and its quality. And all over the world, and first of all, we have to save the lives and health of people, and the construction of the building and the rest of the materials which are inside. So here I would like to focus on people evacuation, and I would like to present you two ways of analyzing it. First one is the typical engineering method, which is usually used during designing process, and it's quite popular and usually used. And the second one is that which we perform here in this project. It's some kind of an statistic analysis. So first of all, the main evacuation factors are asset, so available safe egress time, and RSET, so required safe egress time. So first of all, the required time is the time which we need to keep the egress free of smoke, temperature, and toxic gases, to keep it free and let people to evacuate. And another parameter is the available safe egress time. So this is the factor which focus on that how system or fire ventilation system is working, what are the performance of the environment during the fire in the building. So first of all, we have to calculate these two factors, asset and RSET. First of all, the RSET consists of few parts. First part is part from ignition to fire detection time, so it lasts. Sometimes it can be few seconds late or a few minutes. It depends of the fuel which is being burned. After detection time, we have got time to verify the alarm if it is not a false alarm, if it is the real one. So the system is going to restart a few times and check if it is real fire. Then we have got fire alarm, and we have got time for pre-movement time. So this is the time for reaction, people reaction. And after that, we have got that small part which is from the time of reaction. We have got movement time, and after movement time, we have this is the time from the reaction to the moment when people are in the safe position in a safe fire zone. So this is the RSET time, so that required time, and the required time has to be smaller than available time for safe egress. So, and when we have got these two parameters, we can say if asset is bigger than RSET, that we have got safe system. How to assess the available safe egress time? So we have to define some critical parameters of the environment during the fire, and these parameters should be divided into parts of the fire: evacuation time and time for fire safety brigades. So during the evacuation time, we have to compare parameters as temperature, smoke, and radiation. So the temperature of the hot gases layer shouldn't be higher than 200 Celsius degrees, and the temperature at height of 1.8 meters shouldn't be higher than 60 Celsius degrees. About the smoke, so the density of smoke shouldn't be bigger than 0.1 grams per cubic meter. It is visibility around 10 meters. And the radiation shouldn't be bigger than 2.5 kilowatts per square meter in the direction to the floor. This is this kind of radiation is safe for people during the evacuation time. And the second part is the parameters, are the critical parameters of the environment during the fire brigade activities. So the temperature can be higher, and it is measured on the level of 1.5 meters from the floor, and it can be around 120 Celsius degrees because of the because firefighters have got different clothes and the different ways of carrying out of breathing ways. The radiation can be bigger; it can be even 15 kilowatts per square meter in the distance of 5 meters from the fire, and 5 kilowatts per square meter at the distance of 15 meters from fire. So it allows fire brigades to come quite near to the fire source and to extinguish it. And of course, another question is access to the fire source, some kind of ventilation systems, some kind of a situation with the wind direction. Let us to have the situation that fire source is that the smoke layer is fully controlled, so fire brigades can easily have the access to the fire. But first of all, to calculate the required time, to calculate the available time, we have to make some kind of an analysis of the evacuation time. So we have got two ways. One way is an analytical one for some simple cases. And the second way is to make some kind of a numerical calculation, as you can see here. But what I would like you to look at it, we have got here the one of the levels of the car park. That one on the left is fully covered with the cars, so we have all the locations of cars are filled. And the picture on the right side, this is the car park without cars, but we have got the same amount of people. And when we start the calculation of evacuation, and if we compare both times, you can see that the time time of evacuation in car park with cars and without cars is more or less the same. So it's only 3 seconds of difference. So, but we have to remember that in car parks we have got quite huge area, quite simple way of evacuation. So the time of evacuation is not such a big problem, and it doesn't depend so much of the amount of car parks which are in the car park. Here you have got the situation with the car parks where you have got 10% of cars, 30%, 50%, and 100%. And if you compare all these calculations, the difference between first case and the fourth case is only 12 seconds. So the time of evacuation in car park, when we analyze it, and when the time of evacuation in car park doesn't depend so much of the amount of people and of the amount of cars inside that area. But there is one thing which can involve very much for the evacuation time. It's the possibility of it's the amount of the doors where people can evacuate. So, for example, on the pictures on the left side, all the doors are possible for evacuation. On the right picture, we have got 2 doors switched off, for example, because of the amount of smoke, and so it's not possible to evacuate using these doors. And if we compare these 2 times and these 2 simulations, as you can see on the right one, all people have to go to the third doors, so there can be a situation that there are some kind of queues and the time of evacuation is longer, as in the situation for example, in the office area or in the auditorial area, where of course we can have got some kind of influence of the wind on the building facade. But if we compare these simulations with the car park simulation, here we have got more or less the same similar situation when there is a lack of the doors in that area, and there we can find some kind of a queues which increase the time of the evacuation time. The same situation we have got here in the office area with some kind of an open space and small offices, and on the right side with the situation we have got where we have got auditorial area, people are staying in the queue to get out from that area where we have got fire. So this is the first way of analyzing the system, if it is safe or not, and that what we would like to present is that what was done in that project. These are the statistical analyses. So not only asset and RSET are the only method to analyze the safety of the system, but that what we proposed is to combine four variables to compare smoke concentration, so the visibility, to compare temperature, flow velocity in the cross section of the car park, and number of the roads available for fire brigades. So if we take these four variables and compare them, we should receive an answer how the system works and what is the risk of that if the system is working properly or not. And how we did it. First of all, the first step are the smoke mass concentration and the visibility. So we defined that our acceptance concentration is 0.08 grams per cubic meters, and we defined that if the smoke is, if the car park is filled in less than 30% of its area, the system is working properly and it's good. Between 30 and 60% of the area of the car park, the effectiveness is average. If more than 60% of the car park is covered with, is filled with the smoke with the density bigger than 0.08 grams per cubic meter, the system is not working and it's not acceptable. Another parameter is average temperature on the level of on the height of 2 meters above the floor. So if the average temperature is less than 100 Celsius degrees, the system is good. If between 100 and 120 Celsius degrees, it's acceptable. But if the average temperature on that level is higher than 120 Celsius degrees, the system is bad and the situation is unacceptable. The third variable is the average velocity in a cross section. So as you can see here, we have got three ranges of velocity in on that level. If velocity is less than, if average velocity is less than 0.9 meters per second, the system is the situation is unacceptable because the velocity is too low to push the smoke outside the car park. The acceptable flow velocity is between 0.99 to 3 meters per second, and if it is more than 3 meters per second, it's too much because of the risk of increasing the heat release rate of the fire. And the fourth variable is the access routes for fire brigade. It is defined as to verify how many ways we have free of smoke and temperature, which allows firefighters to come and extinguish the fire. So if we have got if we have situation that there are possible, sorry for Polish words, if we have got three ways for fire brigades, the system is working very good. If there is only one way, it's acceptable. If there is no ways for fire brigades, the system is unacceptable. So summarizing all these variables, we can define something like an operational uptime, so which defined in the percentage in how many days during 1 year the system is working properly, and it's a sum of all these 5 variables, so the smoke concentration, the velocity, temperature, the amount of the routes for fire brigades, and of course the external influence of the wind. External influence of the wind on the car park. So, and another part of this presentation, I think I will give the stage to Paulina Jamińska, because she will present the part about the CFD calculation with fire in a car park.
Okay, thank you, Grzegorz. Thank you. Thank you very much. So a word of explanation on the evacuation studies performed in this project. When we submitted the grant, the first idea was to carry analysis for more office-like buildings, conference centers, and so on. So we could end up with life safety being as the primarily assessed variable in the system, which would allow us to draw beautiful FN curves and so on. But eventually it became apparent we need to do an open car park. It's just such a perfect topic for a wind and fire grant. And in the car park, the threat to the occupants is not really that high, which Grzegorz shown. It depends mainly on the pre-evacuation time distributions. However, if the same methodology was applied to a different building, this asset calculation would be tremendously different value. And this is why we wanted to share in here. And the other things, the statistical approaches, those levels, thresholds that Grzegorz shown, this will become important when I will have my final presentation, because then I will put that into use. And for now, I'm going to pass the floor to Paulina. Paulina is a real wind scientist, and she's doing real science. I was like looking at this, I feel my fire science is not real science, this is real science. Anyway, both are, but yeah, this is a proper wind engineering. As I said, we've learned wind engineering since 2015 out of necessity, but Paulina is a trained wind engineer, and we needed a person like this to really make sure that the wind aspect that we do in our project is on the part of the fire engineering that we are doing, which I hope is good. So Paulina, let me find your presentation. It's here. The floor is yours.
Thank you very much. As Wojciech said, I will tell you something about modeling wind effects on buildings, and also, of course, about modeling wind effects with fires. I will start from the basis. You have to know that to perform CFD simulations, we need some basic values like wind velocity, wind direction. We need to know what is the period of time that we are taking our initial data from, and how we will assess them later. And of course, we need to know what part of the domain of interest is. In our case, when we want to take the wind velocity, first thing is to reach for the Eurocode, where we can find some basic wind velocity values. But of course, those basic values are quite high. For Poland, our 3 wind zones, we have values from 22 to 26 meters per second. But of course, those values are only basic characteristic values, and if we want to take into account mean velocity, we have to modify those fundamental basic wind velocity with also the change in the height, and of course with the effects of terrain roughness and orography. And if we do that, we have to check in what kind of terrain we have. We have 4 different terrain categories, and then we can choose one of those values. In our case, we decided to perform our calculations for the 4th category. This is like the city center with high buildings. And based on that, mean wind profiles can be assessed. So here we can see 2 ways to represent those wind profiles that we will put as inlet values for the calculations. And of course, they are different for different terrain categories, and we can choose one of them. So, of course, we have to also decide what will be the wind direction. So there was a meteorological study done for the Warsaw area, and the data that we have from the meteorological stations were limited to 5 stations, and we took the 10-minute average speed of the last 10 minutes of each hour, and the speed was with the resolution of 1 meters per second, and also some gusts were recorded from the last 10 minutes of each hour. And those values can be seen here on those graphs. The blue one is the maximum value, so those are those gusts, and the red one is the mean value. Taking this whole data, we made 9 groups of wind velocities, but we will only focus on the 3 of them. So we have the velocities 3 meters, 5 and 7 meters per second. This is prevalent values for all the cases where the mean value is 3 meters per second. And we of course have to choose the wind direction, and those directions were put into wind sectors from 12 wind sectors, and for those 3 wind velocities and of course one smaller 1 meter per second, the probability of occurrence of a given wind speed was done, and this was calculated as a total number of records in the considered measurement period. We have the occurrences of the all given speeds, and because of that we could make the analysis based on some real data with probabilities. And the next step we've done during the simulation was to choose the area we were interested in. So we chose a city environment in Warsaw with the height of the buildings up to 48 meters, and the radius was 420 meters. Here you can see all the buildings, and on the right there is a little part of it. In the middle you can see a little red building. This is domain with the in the middle that we will put our main interest building there. So the next step is to bring this real model into the computational domain. So we have to take into consideration that this domain has to be built in a way that will not create any blockage. And therefore, the domain was quite huge. We had some values here on the graph that show how many heights of the highest building have to be maintained to have no blockage in the domain. And this is the real domain I've created. And it consisted of 3 zones. In the middle, there is a zone with the car park. And in this zone, we can put various different buildings. And there is a circular zone that will have all the explicitly modeled buildings. And the rest is the square zone with the external boundaries. Of course, the next step was to create the mesh, and I used the surface grid extension technique by Blocken, because this is the technique that can that using this technique we will be certain that the wind flow is not disturbed by any mesh. It's a hexahedral mesh mainly in the whole domain, and the car park or the buildings in this little subdomain in the middle are built with the tetrahedral cells because of the level of detail that is needed. And here you can see how this mesh looks like. On the left with all the buildings, you can see that those buildings were extracted from the ground. And actually, there are no, all of those buildings are a little simplified because of this extraction technique. We had to choose what level of details we have to maintain. And on this picture, you can see the yellow subdomain in the middle, and in our case we have the open car park, and but of course in the future this subdomain has 48 meters, so we can put any building or object we want in the middle and check how the flow will change or any other parameters we would like, and of course we can check the environmental effects of wind. And of course, all of the simulations have to be validated and verified. So we can validate our model, CFD model, with the wind speed distribution and mean wind speed values with the experimental data. And this is the model that was scaled to 1 to 200s, and we cannot scale down the fire. So therefore, we can only check the wind profile and average wind statistics in this validation. And of course, I've done the verification of the CFD model with the grid sensitivity, and turbulence models were also checked. And there were some discrepancies in the results because there was a problem with atmospheric boundary layer speed up at the bottom of the domain. So this is the ABL homogeneity problem. we have the unintended streamways gradients in the approach flow because we have to set some kind of inlet flow that is at the inlet plane, but we have to maintain the same values in the incident flow also. So the flow that is the closest to the considered building. And as you can see on the right, the problem with the speed up with those change in values is a known problem that was countered by many scientists. And in our approach, I was able to use modified wall function, which was based on the aerodynamic roughness Z0. And this was used instead of equivalent sand grain roughness, which is used usually in the standard wall function. And this allowed us to have no speed up in the wind profile, no change between the inlet profile and incident profile. And also the application of driving shear stress was set at the top boundary of the domain to also maintain the same profile as at the inlet. So here are the results from my ABL homogeneity test. On the left, there is a standard wall function. On the right, modified wall functions. So for the standard wall function, we can see how the wind profile changed along the length of the domain. And it can be seen on the bottom image. And we were able to get very good values of similarity between the incident and inlet profiles for the wind velocity and kinetic turbulent energy, and also the dissipation of the kinetic turbulence energy. So after doing the ABL test, I was able to put a fire in my domain, but of course it wasn't literal fire, and I had to simulate it as a volumetric source of the heat and mass, and no chemical reactions were actually modeled. But the heat transfer was, of course, applied in the model. And the simulations were, of course, done as a transient flow and with the Ran's equations and RNG turbulence model. I would like to summarize how this was done, because maybe it will be easier to get a grip about this. So at the beginning, it was the geometry import, and I had to do the import of the whole domain with the explicitly made buildings. And then was meshing, building the case in the Fluent, assigning the interfaces, of course, and at this point, making the ABL new wall functions definition. And then I could go to the next step, CFD calculations. And those were repeat steps, because we had different cases with different wind speed and wind direction. and those calculations also had the fire in them, and they were done for different heat release rate. And in the post-processing, you have seen some of the data. We can take the temperature, smoke, velocity, statistics, and see all the important things as a data or as images. Overviewing the whole project, we've done in the main series 336 simulations with the open car park and the implicitly modeled area of the city. And the additional series had the warehouse instead of the open car park in the middle subdomain. And the additional series B will have 144 simulations with the open car park, but the city modeled explicitly. And in all those cases, you can see that we had various heat release rate, wind speed, and 12 angles of wind attacks for each of them. Here are some results of the wind distribution, wind speed distribution inside our open garage. So you can obviously see that for the angle of the wind attack equal to 0, the wind goes through the building, and the velocity inside is higher with the higher velocity at the inlet. But for the 90 degrees, where we have a wall from the incident flow, there is a stagnation point observed, and it's in there even at the highest velocities with 7 meters per second. And when we look at the visibility of smoke inside the car park, so on the left for the 0 degrees, there is near perfect outcomes for all the fires because the smoke is blown out from the car park. And for the 90 degrees, the smoke accumulates and doesn't leave the car park. And this is this can be seen for all of the heat release rates, but the most significant for the highest one. Of course, we modeled the surroundings of the building to check how they will impact the flow inside our car park or other buildings. So in this case, you can see how there is an unexpected flow path on the right, on the bottom picture, where the flow changes, and there is it will influence the outcome of how the fire will behave inside the building. This is the building of the warehouse, and this is how the wind behaves inside. We can see the vortices inside the building, and even the small change of the wind of the wind angle can change how this wind will behave inside the building. And of course, the similar results for the car park, and those velocities inside the building may also help to assist the evaluation of conditions. of course, we can think that even without the fire, we can take some knowledge from this simulation and make some assumptions. Thank you for the attention.
Thank you, Paulina.
Thank you.
So I'm really excited now because now everything that has been building up for the last 2 hours can be put into one final evaluation. As you have seen, we've done a lot of CFDs and a lot of studies, and it has been a big challenge in how to actually process that. By the way, in the meantime, we have received one question by Anas, was the terrain modeled in the model. So Warsaw is flat as a table. I can tell you we did model the terrain of Warsaw, but no, the simulations were very flat. It's interesting to add the terrain into the account, especially that it will change your flow paths tremendously, whether you're upstream or downstream a mountain. And also, when you do that, you perhaps would need to resort to more complicated models to receive the initial profile of your wind, because perhaps then the simple logarithmic profiles will not be sufficient to describe the wind velocities around mountains or complex terrain. So you may need like WindSim or some other more complicated tool to first define the wind profile. So, as we build this all up, we've carried out hundreds of CFDs. We've defined the boundary conditions to the best of our capability. We've gathered some interesting data on occurrence of fires in Warsaw, on the local car parks, on the built environment around. We've built a mock-up of a city. We've built our own models to modify the wall functions to get better control on the wind profile. Now, how do we all proceed this and get answers to the questions that I've defined at the beginning? We would like to look at the consequences to the people in the fires, which actually, as Dr. Krajewski said, is not that impactful in a car park scenario, because here the real variable that defines the evacuation capability of person in a car park fire is their pre-evacuation time. That's the variable that will determine how quickly you can escape the car park or not. And the changes that are caused by the presence or not presence of the wind will not be that significant. If we did choose a different case study, like an office or an assembly hall, this would most likely be quite different, because if you have queuing in the doorways, there will be significant delays in the evacuation time, and then having the wind effects push the smoke somewhere could be actually significant. In this presentation, I'll focus mostly on losses in goods. For example, vehicles in the car park. These are significant losses in all car park fires. The losses related to destruction of the building and to some extent the damage to the environment. So let's start with the chronology, the warehouse fire. The warehouse was a model that we've built even before we've started opting for the project. It was actually a case study that we've built to justify the project. And then when we got the project, we could use all the interesting post-processing tools that we've developed to analyze the outcomes of this study. It was a warehouse in a city environment. We did a full rotational analysis of 12 wing angles and 2 velocities. And we were looking into the performance of a smoke control system in the warehouse. It was equipped with natural ventilators on the roof, so obviously this will be impacted by the wind effects around. And here is the unnecessarily large table with the results of this analysis, and just the middle column is interesting. It tells you the rate of mass flow through the natural ventilators compared to the conditions where there was no wind present. So no wind is 100%, and in other wind conditions we have less or more, from 70 to 158%. And investigating those results, looking deeper into analysis that we've done, gives quite interesting quantitative analysis of what happens in the case of a wind in the building. So we have the worst case scenario that occurred not at the highest wind velocity, but actually that happened at 5 meters per second. 70%, that's the biggest reduction in the performance of smoke control ventilators out there. We've wondered why, because it's obvious that it should be in the highest velocity that would worry you the most. That's our current paradigm that we use in our design, larger wind velocity, worse performance. Why it happened at the lower velocity. And the explanation comes from investigating the patterns around the building. So if we have the low velocity, 5 meters per second, these flows happen in such a way that the building is quite well isolated from the wind. So there is almost no wind flow around the building. It's very stagnant in that location. However, if the wind speed increases to 10 meters per second, we suddenly start finding some flows that happen around the building and eventually hit the openings in the building. And through those openings, they influence the performance of smoke control ventilator. So it's not just the velocity, it's not just the direction of the wind, but it's the particular outline of the flow path in the vicinity of the building that dictates the performance of the vent. A very interesting observation, and if we have not done that, I would not believe that it can be actually worse in low velocity. It's obviously not always like that. In many cases, at larger velocities, we had different outcomes than in lower ones. So it's difficult to say which would be the worst one. And another interesting observation is there's two cases in here, 240, 270 degrees. 143%, 158% of the performance of the natural ventilators in the buildings, they are turbocharged in this scenario. First, I thought that's a mistake. They can't go that well. Like in wind conditions, they should be worse than in the reference case. And here they are not just better, they are considerably, like half better than the normal vents. And comparing these to scenarios at low velocity, these do not show such a performance. So we were wondering what happened that this performance was possible. And there actually is an answer to that. If you look at the flow path again, we have wind that flows through our domain, and it flows around the buildings that quite tall nearby the warehouse that we're modeling. And there's a building in here. This wind pattern hits this building, bounces off this wall, and goes directly to the inlet of our building. In large wind velocity, it's like supercharged jet that is hitting directly into the makeup air provision for the building, making literally a flooding system for the warehouse, pushing out the smoke with extreme capacity. A very interesting outcome. And if we were just analyzing the building without the buildings, without the terrain, without anything around it, we would never find out this particular outcome. It's very interesting, and it shows that even if we try to simplify our modeling through implementation of ABL models, which are much cheaper to run and much easier to run and give you quite good rough outcomes, these specific things can happen in your locations, and you should be at least aware of the particular wind field that you're dealing with in your vicinity. The next thing that wind is significantly impacting is the external plumes. So again, we have investigated the shapes and sizes of the external plumes by putting an isosurface on them. We had plumes that were near perfect, very nice thermal buoyant plumes that simply flew away from the fire. We had plumes that were quite complicated and were accumulating behind buildings. I'll discuss this a little bit more. And we had specific wind directions in which the plume did not go upwards, but it go down, like in the experiment that I've shown at the beginning of the previous presentation. So we have the smoke spreading across the floor of our model, actually in the vicinity of buildings. If you look at the smoke concentrations, it looks quite dangerous because the courtyard of this building, which is 50 meters away from the fire, has actually larger smoke concentrations than the surroundings of this building. It's quite challenging. This tool, this approach, analyzing the near field of the building model that you're analyzing in wind and fire coupled modeling, allows us to for interesting observations like that. Another one that's interesting, I went to we have a city model down here in the office, and I went for my tall building that were nearby. Actually, it's that building that I'm holding. Anyway, the interesting thing with tall buildings is that if you hit them with wind from your direction, there will form a vortice behind the building. Like there will be two vortices. that are forming behind this building, like a shade behind it. And what's interesting about this shade is that if there's a smoke plume coming in this direction and the smoke enters this shade, these vortices that are behind the building, it can be quite efficiently trapped in that location with no possibility to be extracted from there. And this means that even at a large distance from the fire, you can actually observe a significantly higher smoke concentrations than in the buildings that are nearby because of those aerodynamic effects. Another good reason why we should study wind engineering when we're doing fire engineering. Those things are not obvious. Wind is a complex phenomenon and we should treat it like that. And while contemplating this is a perfect way to assess the near-field damage made by the fire to the environment. If you would like to perform an analysis, risk-based analysis on the damage that the fire can cause to your environment, analyzing stuff like this, how far the smoke can spread, which will be the area in which people are endangered, Bartosz is actually quite good at implementing this with Global Information Systems, GIS, where you can put number on how many occupants are in each building. You can literally, from this simulation, tell how many people in each of the scenarios is endangered. This is something very good for preparedness stage, where you place a building in a new environment, or perhaps in recovery stage, where you had a massive fire in your city, and you would like to determine which part of the city can be the most contaminated. So this kind of tools can be very, very helpful in assessing the environmental damage, and using CFD as your tool for near-field wind and fire coupled analysis is the way to go. The next step, as I said, warehouse is where we started. That was already a lot of findings, but here we go to the proper analysis, the car park. Like Paulina previously mentioned, we have flows in the car park that determine where the smoke spreads in the car park. When you start looking at those pictures, you start to see patterns. If the smoke goes left to right in my car park, my fire is here, I have a triangle shape which you would expect blowing on the fire. If I have almost no velocity in the car park, this is the stagnant case where the wind is coming from the bottom and blocks everything inside, the whole car park is smoke lodged. If I have large vortices forming inside of the car park, I have shapes that reassemble those vortices in my plots of the smoke in the car park. Actually, I would even say that to tell you what would be the outcome of a fire in this car park, I probably would not even need this picture. Based on the hundreds of CFDs that we've made, observing the patterns of velocity and how those translate into the patterns of smoke distribution inside the building, this is pretty much what you need to define the performance, most of them. Maybe not perfectly, but it should be enough. So it gave us this interesting idea that perhaps you should just run multiple analysis for the wind field, for the velocity themselves, no fire in the car park, analyze those, and based on those simulations, pick up 2 or 3 scenarios that you really need to simulate with the fire inside. This could be a very clever trick to really reduce the number of CFD analysis that you need to perform. And the wind analysis, when there is no fire inside, would be significantly cheaper than the analysis with the fire inside. Significantly, 10 times cheaper for us. Another thing, the temperature field. I'm receiving your difficult questions. Good. Good, a lot of good questions. I appreciate that. Keep sending them my way. Another thing, the flows and the temperatures. Here, as before, the wind patterns, the flow patterns will define how much of the heat is removed from the building. This is smoke and heat extraction system, so heat is being extracted. And in some cases, it's not. When the car park is blocked by the wind and there is stagnant flow field inside, you can see the heat accumulating in the car park having much bigger area than when the fire is ventilated very well. You can actually analyze this much better when you compare the same fire but different ventilation rates. You can see that at 1 meter per second, this is a 9 megawatt fire. At 1 meter per second, this is not enough. The fire is clogging the car park, while when you increase this to 5, 7 meters per second, you clearly have empty from smoke car park, very well ventilated space. And when your car park is blocked, actually the low velocity is better because the smoke can escape the car park easier, while when there's the high velocity, it's blocked more. So it's more entrapped in the car park. Different outcomes at different velocities, the same fire, the same car park. Based on this analysis, we can technically determine the area at which the fire may spread or damage surrounding vehicles. With this knowledge, we can try and map the risk of the damage to the goods stored in the car park, meaning the vehicles around. So, as Bartosz said, now all the pieces that we were building start coming together. As Bartosz has presented, he found out the probability of fires in the car park, he found the probability of the cars being inside the car park, and by the way, these two things work together, so if there are no cars, the probability of fire incident inside the car park is low. The probability is per vehicle, not per car park. Based on the amount of vehicles that can be inside, we were able to determine a general probability of a fire to happen inside the car park. Based on that, we understood how many cases led to outcomes in which the fire could spread. And based on those outcomes, we could assign a probability that the fire could spread to the surrounding vehicles, multiply that by the damage done to the vehicle, and voila, you have the risk of damage done to the surrounding vehicles. A very useful thing. Another thing that we have investigated, and I think this is some sort of novelty in here, is the access for firefighters. This is very important for me. We need to understand if firefighters can enter the building. And it's not just the number of entrances. If they have all entrances available, like in this case, they can approach from 3 different ways. That's the most perfect solution. Wherever they go, they will find the fire. If they can approach from 2 ways, I still find this a very good approach, possibility for firefighters. However, if they only have 1 pathway, this means they can pick a wrong one when they arrive at the scene, and in consequence delay the effective water extinguishing action, which will mean that we will deal with a larger fire with more severe consequences. If there are no entrances to the car parks available for the firefighters, they will not be able to perform their actions, and they will be limited to acting from outside of the car park, which we know is not often very good when the fire is deep inside. So we took a lot of effort to actually determine if they can access the car park or not for all the scenarios that we have investigated. And now we come to an attempt on how to assess this at large. So we have done 330 simulations for those car parks. How do we process the data all together so it makes sense? So I can, instead of producing a book having 1,000 of pictures, have one nice clean plot that tells you how good or bad is the car park. And this is a place where everything we said so far comes together. So we are analyzing the visibility, temperature, velocities, firefighter access in the relation to the probability of wind, and trying to assign when does the car park work or not. First, we assess the visibility. This is an estimation of how big part of the car park is flooded by the smoke. So we've put our threshold values, 30–60%. These are numbers that we just came up with. We don't have, that's just an idea, whatever the number is. We assume that if the car park is filled just in 30% by the smoke, then the outcome is quite good. If it's filled in 60%, it's not great, but also not horrible. And if it's more than 60% filled, it means that most of the car park is filled with smoke, and this is an unacceptable outcome of the simulation for us. So once you can apply this statistical method to a single case, you can apply it to any amount of cases that you want. And finally, we are capable of investigating the outcomes of multiple hundreds of CFD simulations altogether. And we start seeing some patterns emerging that you would not see if you only looked at individual cases out there. So if we look at the smoke flooded area for 4 megawatt fire, for low wind velocities around 1 meters per second, in almost none of the cases the system works. Most of them, the car park is fully filled with the smoke. At 3 meters per second, we have some cases in which the performance is not that bad, but most of them are still bad. And at the largest velocities, we see a lot of points where you have very good performance, mostly, and some points where the performance is very bad. With this data reduction, we're capable of investigating really hundreds of CFDs and quickly telling which cases are worse, which cases are best, and what is the quantitative difference between between them. That's for the smoke flooded area, the visibility. Next one, temperature. Temperature is difficult because the difference between the different fires will be larger than the differences between different winds. So you cannot compare the 1 megawatt fire to 8 megawatt fire. These are completely different stories. But you can compare them within a group of designed fires. And here we also assume that there must be a temperature at which we are comfortable with, which was the average temperature below 100. There was a temperature at which we were unhappy with the car park, which was above 120. And there was some medium region between 100 and 120. And we assigned colors to the scenarios in which those criteria were met or not. This will become important later. Similar thing was done for average flow velocity. So we assumed that if you have a flow velocity below 0.9 meters per second, that's bad, because that's insufficient. If you have velocity above 3 meters per second, that's also bad, because that's perhaps too much. You can affect the fire growth by this wind flow, and actually can accelerate the fire or spread of the fire. So we also don't want too high velocity. So we've assigned those numbers to the criterion, and ended up with another matrix of good average and bad performance of the system. The last one, access for firefighters, again the same approach. We investigated the cases, how many entrances there are per scenario, and for 0 we gave the bad outcome, 1 to 2 entrances it's average, and 3 entrances is the perfect outcome of the scene. Those indexes were assigned. By the way, in here we have one little problem. As you can see, the larger velocity easily meant that the access routes were better, but the velocities were above our threshold. So do we want to keep the velocity under control, or do we want more access routes? It's a challenging question, because we don't really model here the impact on the growth of the fire of the large velocity that we put into the car park. Perhaps it's not that severe, perhaps in the road tunnels it's a much bigger problem, but still I wanted to highlight that this assessment is not just that simple. Anyway, we've done this assessment of different thresholds for the visibility, for temperature, for flow velocity, and for access for firefighters. Now, how to put probability into that? We came with the concept of operational uptime index. We define it as the percentage of time in the course of a year in which the outcomes of the fire would be acceptable. Like, if we know that the western winds are 30%, the northern winds are 17%, the eastern winds are 7%, the wind velocity of 7 meters per second is this, and so on. If we know the probability of wind over the course of the year, we know outcomes of all the fires that can happen in those winds, we can actually tell for how much percentage of the year the car park is ready to operate when there's a fire happening inside the wind. So first, we've averaged all those outcomes of individual scenarios, of individual assessments of visibility, velocity, temperature, and firefighters' access into this one major table showing the final index of operational, non-operational, and average. Then, knowing all the probabilities, the things that Paulina said, 5 meteorological stations around the world, so historical data from 50 years, a very good understanding of what the wind in here looks like, we could assign those probabilities to the points in the table, and here we go. We have the operational uptime index measured, and this allows us to actually go into a very nice and clean way of presenting this outcome. Because now I know that if my heat release rate would be 1.4 megawatt, which is a small fire or an early growing fire. Bartosz shown that this is just the 5th percentile of all the fires that were tested in laboratories. I know that in these fires, for 86% of time, my car park is ready to operate, and it will operate efficiently if the fire happens there. And in 11% of cases, it would be to some extent inoperable. If we increase the size of the fire to 4 megawatts, the number would be 40% almost for the good operation and almost 60% for the bad one. For the largest fires, 8.8 megawatt, that's top percentile, 95th percentile, we have 14% of cases in which the car park operates properly, and 83% cases where if the fire happened in those wind conditions and this heat release rate, the car park would not be assessed as working correctly. This allows us to process hundreds of CFDs into single index that you can tell to someone, hey, your car park works only in 15% of cases. That's not good, right? Or your car park seems to be working in 90% of fires that can happen in it. That sounds quite reasonable. This is a very nice outcome of a very long and painful and complicated analysis. Anyway, this is of course related to the direction of the winds, because the direction defines the probability of the winds happening. And if you think that I have in a way cheated my way by making this look the worst that I could, you are probably right to some extent. I did. We also did an analysis what would happen if the building was rotated against the wind. Would it shift the operational index a lot? And here are the outcomes. This analysis, after you have done everything so far, is actually quite easy because you're doing that at the post-processing level. You don't have to repeat the simulations anymore. So you can see that there are cases in which the operational index could be very low and cases in which it would be very high, depending on how your building is positioned against the windrows. We've carried this sensitivity study for all of the fires and came up with these distributions. I think that they are very interesting. Finally, risk of extreme fire. Bartosz shown that motivation for this study was the extreme fires. We had cases of extreme fires happening, like in previous months. I have a feeling they happen every month. Like seriously, in the last 3 months we had 3 major car park fires. It's insane how often they happen, really insane. And we wanted to assess how often a fire can happen that could actually take down the building. To assess that, we need some elements. First is the probability of fire, which Bartosz defined for us. The second is how many vehicles are there in the car park. So if the car park is empty, there is no fuel to spread, so that there will be no extreme fire in it, right? The third one is how big is the initial fire, because it will define the probability that the fire can spread consequently before the firefighters arrive. And can they actually arrive? Can they actually reach the fire when they arrive? That's another variable that you need to account for. If you have car park for which the fire brigade cannot even enter, there's a probability that even if you start with a small fire, it will grow to a size where it will be possible to endanger the structure. So let's try to put some numbers into that. First, we know how many vehicles are there in the car parks from the statistical analysis of Warsaw Park and Ride car parks. And we know that per day, work days, per weekends, we know at particular hours how filled are the car parks. So we have a number on how many vehicles are there. We know, we don't know. We would love to know what's the distribution of real vehicle fires in the real world. I would love to know that there was 1,000 car park fires in the world and the distribution of the heat release rate of the initial vehicle was like that. It's simply not possible. We don't have that data. All we have is the experiments carried in the laboratories with the caveats that Bartosz has mentioned related to the location where the fire is ignited. However, based on those data, you can say that in 60% of those experiments, the fire was 4 megawatts or less. In 10%, it was more than 8 megawatts. You can put some numbers to some specific scenarios, analyzing the table at large, and come up with some probable fire sizes, and then knowing the outcomes of the fire for each car park fire size, design fire size, which we have carried before, we can know the outcomes of that. Now the last one, can fire department reach the fire? First, they need to be notified. So we put the probability that the fire alarm is working in here. And the second is that the firefighters must access the building. And that's exactly what we've done in the risk analysis previously. So we have a number to say in how many cases they could access the floor and in how many cases they could not if the wind was taken into the account. Taking all of those together, we get a combined probability of fire annually in a car park that could perhaps endanger the car park of 3.2%. It sounds quite high, but in general, the probability of a fire in the car parks would be 1 in 20, 1 in 30 years. So the number is not that off from what I would initially thought. I'm surprised that this is the catastrophic fire size, actually. Anyway, this could probably be narrowed down if we included the location of the parking spots, the floor at which the cars are located, the weather, temperature, moisture. This will impact the growth of the fire, the vehicle size and age, the vehicle type. There are multiple variables that we could add to this probability analysis to narrow down the risk of an extreme fire and come up with a number. And then to get from this value to the risk, you need to know the value of the building. Just multiply it and you have your risk in terms of dollars. So that's how this complex methodology can be narrowed down to give you a single number, single value of risk. And with risk, I'm an engineer, I can work with risk. I can work to reduce it, I can accept it, I can tell we need changes. This is a variable that I feel fit to work with. Now with all of that been done, let me take you to some final conclusions of the project. So the obvious one, wind affects the consequences of fires in buildings. I mean, it was obvious from the beginning, but now I have some very good proofs in how much it does, so I'm very happy with the outcomes. The second one, incorporating wind into multiparametric analysis is possible, but it takes quite a significant amount of work to be done properly. It's not easy, so you need to go through some specific steps to get the boundary data and initial conditions that allow you to carry those analyses. We had a working hypothesis. There exists a minimum wind speed above which wind effects are insignificant. I don't think we confirmed that. I think I cannot confirm if their value exists and what is it. The local wind field caused by the buildings in the vicinity of the fire will make such a complex spatial arrangement of wind flows that it will not be possible to just define a threshold value. We defined some very interesting qualitative and indexing methods to analyze the outputs of the analysis at large, which I think can be very useful for future analysis, and we will be definitely resorting to those in our future studies. We also found out how to reduce the number of the scenarios to be identified, because this is expensive. There's a reason why I'm doing this as a scientific project funded by the National Science Center in Poland, not as an everyday commercial job. It's just too big to be a single job. 172,000 CPU hours. I'm not sure if you noted that number from Paulina's presentation, but that's the number of computer hours that we've used to run the calculations shown in here. And lastly, the CFD is a perfect method to assess the environmental damage caused by the fire in its vicinity. I really like this method. There's a chapter in Margaret McNamee's and Brian Mitchum's handbook about environmental effects on fires and modeling them, where we go in details on that, and I think this is the method you should use. Now, some sexy stuff. What should we do with this in the future? I have two future trends. One is I regret that we are unable to capture, these feedbacks. Systems and growth, the wind and growth. We're simply unable to capture how the wind impacts the growth. We still have a design fire scenario. I would love, and perhaps I'm inspired a bit by traveling fire methodology, I would love to invent or come up with some method that would allow us to build a growing fire that the growth of the fire would be the outcome of the analysis, not an assumption done before the analysis. I think it would be super interesting, and if we could couple that with the finite element model of the structure of the car park, that would be beautiful. Perhaps a subject for the next grant, because we're finishing this one in next week, so I'll have some more time to spend on science. And lastly, those analyses are costly. Like, they're really costly and they take such a long time. Like, just building the mesh with the extrusion technique for this model of the city, it took like a month. And it was just a month of working on that. So we need to find some clever ways. One is to reduce the number of scenarios that we are having, which was discussed to some extent today. The second one would be the use of GPUs, graphical processing units. It's something that we've invested in ITB, and we already see it can accelerate the CFD process by 10, 20-fold, allowing us to run significantly more CFD analysis than before, and actually do those kind of analysis more cheaply. And the third one, perhaps the most exciting one, is the use of AI. AI to predict, based on the velocity or pressure fields, the outcomes of the fires inside of the buildings. And if we could come up with such a models, it could enter the general industry and be very helpful for many people. So I am literally flooded by questions, so I guess I should stop talking and start answering. So let's try and do that. So thank you for this section, and let's try to tackle some of your questions. First, Javor Panev, was changes of wind conditions, velocity, direction during the fire event being considered? Thoughts how quickly the system will respond, recover? No. Like, come on, it's 300 simulations with a steady state, and you ask about changing them. It would be very, very time-consuming and challenging to introduce the changes in ventilation pattern. There are interesting studies from Fire Safety Research Institute how changing the flow path in the buildings, residential buildings, has changed the outcomes for firefighters. And there are some cases analyzed where their life was lost because of the phenomenon that you describe. Very interesting cases. I think if we got to AI, you could actually do that very easily, and it would be very interesting. How quickly can the system respond to that? I don't have an answer to that, but this is something that we work on tunnels, by the way, with my other student, Jakub. Jakub is doing his PhD on tunnel ventilation, and there we solve the momentum transfer in the air inside the tunnel, basically calculating how long it takes for air to stop, reverse, and go somewhere. And it takes minutes in case of tunnels, but tunnels can be kilometers long. In terms of buildings, I think the response would be fairly quick. The next one, Szymon Matkowski. Szymek is always asking a lot of questions, architect questions. If you find them unprofessional, just omit them. Okay, no, just kidding. Evacuation part. How many different fire locations were analyzed in the system design? Not that many. For evacuation, we didn't even go into the location of fires. We just were closing doors. So we just assumed some pathways blocked, and that's related to the location of fire, but fire is not explicitly there. So we were testing for 1, 2, 3 escape routes. For fires itself in the car park, we've tested like 5 or 6 locations just to have a basic idea if it changes the outcomes a lot. It does not. The one that we've chosen was perhaps the worst one. So we did not investigate it that much. Again, if we had access to AI back then, that would be great. CFD part, what detailing of the facade is required to be presented by architect to conduct proper CFD simulation? Most of car parks are not just open, especially in the city center. Yeah, you're correct. In our case, perhaps the cameraman can zoom. That's how the model looked like. I'll just go closer. That's the car park that Is this good? Okay, this is tricky. Okay, so this is the car park that we've modeled. As you can see, it doesn't really have detailing in the openings. There was a discussion that introducing a porous medium inside those openings would significantly change the flows inside the car park, and we have actually published a research on that like 1.5 years ago, where a porous membrane has reduced the flow inside the car park by half. In this case, I'm not sure if you want to reduce the flow or improve the flow, so it's difficult to say. I would say anything that goes into those openings, whether it be porous membranes, lamella, whatever you put in there, it will have a significant impact on the flows inside and should be modeled. If you are using a proper CFD software, that's bad to say proper. If you're using detailed computational models, you should be capable of capturing those effects, and you should include them in your analysis. They can be significant. What is the criteria for area to be analyzed in terrain? Yeah, it's a huge terrain. The reason was that you will, when you have your highest building in your domain, now I'm going for my highest building in my domain, this bad boy. This one was 48 meters tall, and what you need is 15 heights of this building till the edge of your domain. That's what drives your domain, and because we're rotating it, we want this 15 heights in every direction. This is what drove the insane size of the domain. But by the way, the size of the domain is not such a big issue because the mesh that is used in the far away parts of the domain is very coarse. It's like 5-10 meters mesh. You don't need a very fine mesh besides the boundary layer to have. So it's not that expensive to actually make a very huge domain, and it does make a difference in your CFD calculations. However, you must be aware how ABL model can be impacted by the roughness of your ground, because as the wind flies through 2 kilometers of your domain, the interaction between the wind and the terrain will change the wind profile. This was the entire challenge that Paulina went with, introducing her own enhanced wall functions for the terrain to make sure that the profile that we receive at the car park is the exact one that we introduced into the domain. Okay, I hope they answered that one. Come on, Shimon, another one. Do you think that wind smoke patterns should be mandatory in city centers? That's a challenging one. That's a really tough one, because technically if you put a new building inside the city center, you change the wind patterns for all of them around. Like, it's not just the building that you're building, you're changing everything in your surroundings. We have a funny thing in ITB, the building that we are in, because just next door there is a quite large building built 20 years ago, and it changed the wind flow patterns in this region, and there is insane wind anomaly as soon as I exit the doors to my building, where the wind is like 3 times quicker than anywhere else in Warsaw, and that's how the other building has changed my flow field. So I'm not sure if it should be included in city planning. There is studies related to pedestrian wind comfort. You don't want the skyscrapers to blow out the pedestrians that are walking near them. So that's a part of analysis. Perhaps something like that could be done with CFD for fires. It's an interesting concept. Again, I think as soon as we get AI for quick analysis of multiple cases, we could be doing this very efficiently. Another one, anonymous. Any thoughts on accounting for the effect of wind of the fire scenario itself? Yeah, I would love that. I would love that. That's the dream. And I have in my head the pathway how to get there. There is a PhD by Mochtohir. He is now in Spain. It was a PhD done in Canterbury like 10 years ago, and he has investigated the parameter called the flux time product. And that's basically a sum of heat that has to enter a part of the vehicle to ignite it. A way you can assess if you can ignite something or not. And you can use that to actually track if the fire can spread to other cars or not. Then it's the case, where does it spread? To the interior, bumper, tire, gas tank, whatever. It's challenging, but you could do that. And once you get that, you could perhaps build a model to simulate the growth of the fire of the vehicle itself. This flux time product, by the way, I had an interview with Rory. Rory told me it's bullshit, so I'm not sure if I should recommend that. But I kind of like it, and I resonate with that concept. And perhaps one day we would have that. That would be beautiful. I am working towards that. That's my dream to have. At this point, the best thing we could do is just find a reasonable definition of design scenarios and go with those. Benjamin Koo, hey Ben, have you observed any vortices forming behind a building that impacted naturally ventilated system? So in this case, no, because we didn't have buildings that would be very prone to that. But I had a case study. Let me take my favorite building. We had a case study in ITB where we were investigating, should I come closer, a fire in a corridor of a building, and there was like opening on this facade that led to the corridor. There was opening on the opposite side of the facade, and there were some patterns where the wind was hitting here that were creating vortices behind the building and creating overpressure in this location. And we expected that it will be very well ventilated from this opening to this opening, because this is cross ventilation, but in fact it was blocked. So a very complicated wind case study, and I've seen wind blocking natural ventilations on the behind of the building. Definitely it can happen. Another good reason why you should put CFD into your analysis. Another one from Ben. Have you also extract low conditions from Fluent and implement them in FDS in smaller domain but higher resolution? If so, have you observed any additional observation differences? So no, we have not. We have used only ANSYS Fluent for this modeling. The internal domain where we modeled the fire in the buildings was actually quite good. The mesh resolution was quite high in there. The entire model had like 50 million. How much was the model with the city, Paulina? Like 50 million cells? 16. We need to build a bigger model. That was 3 years ago. 16 million cells for the entire model. So it was good mesh inside. We did not export anything to FDS. We have not used FDS in this project for our own preferences in software. We are basically ANSYS Fluent users, and the ability to run multi-CPU simulations in our optimized for ANSYS environment is the way to go for us. That's personal preference, nothing else. it could be interesting to use FDS. There is a wind boundary condition, mean forcing concept in FDS, that there is the roughness concept implemented in FDS. FDS has the tools that can help you simulate wind. And there's also a wind case in FDS files. If you go to examples, you will find FDS wind case. It's a small domain with some buildings inside, and you can play with that. So definitely FDS is capable of doing that. We have not chosen to do that. Next one from Ben. Understand that high velocity has an impact on fire growth. I'm wondering, where is this measured? I imagine high flow circulation within the compartment, but low ventilation in the building is not going to grow the fire due to ventilation limited fire. So we've touched multiple things in here. First, are we talking about a single object, like a vehicle burning inside the car park, or we're talking about fully developed fire, which will be two completely different cases and two completely different wind impacts? In this project, we resorted to growing fires, which means there's an object inside the car park that is burning, and we're referring to that object. Now, where has been the velocity measured? I think the first place I saw it was in Ricky Carvel's PhD. Kuba, correct me. The velocity impact on fire size. That's Ricky Carvel's PhD, right? Yeah, I think it was Ricky's PhD. That's a long time ago, super long time ago. And since then, it has not been very well established as a relation. We are studying this with Jakub in our research on tunnel fires again. That's a place where we really are intrigued in the relation between the size of the ventilation, the velocity of the ventilation, and the size of the fire. But in here, we could not do that. 3 meters per second is really just a threshold I've put in here. It could be a different number. I don't have a perfect citation for that one. Another one, anonymous. The internal flow may not be good direct measure for whether the results are acceptable or not. Its impact is indirect and implied. For example, that it will affect the smoke movement, which is already accounted for. I can see it as a proxy, so it might be better to just use upper bound. It's interesting. I wouldn't say it's the ultimate, like I would just do the air velocity analysis and not do anything else. No, I would not do that. I would rather do air velocity analysis, and based on those results, I would choose my next steps. That's what I would do. And also, if we transition to AI, actually, if you have a fire models with known velocity field as your training set, and then put new velocity field as your variable, you could put new fire in there, and it should be accounted for with all the interactions in there. That's a bold statement, and there's like 5 years of research to have this as a product, but you could probably do that, and I would go this way. Not as an ultimate assessment that, okay, my velocities are like this, we are good. No, it won't work because of the interactions that you've mentioned, the ceiling jet and stuff like that. However, I think it's a good indication when you want to reduce the number of your scenarios, because running hundreds of scenarios is costly, and we not always can do that. There's also an interesting physics in momentum transfer between the sailing jet and the flow of air underneath it, but that's a topic for another discussion. Anas, if the person of probability is so low, what do you recommend to improve the situations? I would put jet fans in there, really. We're about to do a study as soon as we finish the project. The next step, which will be done in our internal research grants, is to put jet fans in the car park and see how easily the jet fans could control the situation. And I am 100% sure they could do it perfectly. Then we come into the operational performance of jet fans for sure. So how often they act, how often we can trigger them, at what wind they stop acting, what's the minimum amount you need, and stuff like that. But I'm sure the mechanical ventilation could really work well in those car parks. And I am really horrified by the low results of operability of those open car parks. It's really bad. And the probability, 3% for catastrophic fire yearly. Like the first time I saw the number, which Bartosz brought to me, and then I calculated with some own stuff, I thought it's a blatant error. Like it's such a high number. They've redone the math like 3 times, there's no error, that's the number we get. The car parks are really dangerous places, to be honest. So I would resort to mechanical ventilation in here. Another one, 3% probability seems very high. It implies that you have 30 car parks in the city. On average, you would get 1 potentially catastrophic fire per year, which feels too high. Yeah, going back to this discussion, it feels high, but again, if you think about a car park, I would say that having a fire in a car park from 1 in 20 to 1 in 50 years, that doesn't shock me. And 1 in 20 is 5%, 1 in 50 is 2%, so we're in that range. And catastrophic fire, in this case, in strong winds, there was almost no scenarios where you would not have a catastrophic fire, because in every scenario, the car park was completely filled with smoke, which means that firefighters could not enter, it could jump between vehicles and so on. So that's the reason for high probability. As I said, the number could be refined by entering more variables into there. The location of the vehicle, the floor, the humidity, temperature, etc. Perhaps we should also narrow the probability of the fire itself and the size of the fire, the initial size of the fire, based on the experiments carried without the source of fuel underneath the vehicle. This would also change tremendously. And you could also put time into the factor, like what's the probability it will happen in 10, 15, 20, 30 minutes, which could be refined to the time of arrival of firefighters. Then you would probably get different numbers for different timings, and you would perhaps get more optimistic or maybe realistic number. I wanted to share it in here to just show that you can come up with a number following this methodology. I'm not insisting that it's a perfect number. It's a number that kind of scares me. It is what it is. Final one, Shimon. Do you think not wind speeds of frames influencing the fire, but is it possible to define standardized view on patterns the future designers may refer to? I don't think so. I think it's too individual for each building. It's too complicated to just have a pattern-based collection on what's a good pattern, what's a bad pattern. I wouldn't go that way. I think the analyses are cheaper and cheaper and easier. We should go with them further and build up them and have better tools instead of relying on simplifications. Are you concerned that jet fans could make the fire spread worse? That's a difficult one. Again, coming back to this 3 meters per second velocity. So I remember after Liverpool, I've done a CFD study of jet fans in car park, of a car park similar to Eco, and I've done a 20 megawatt fire. And indeed, they changed the shape of the flow field and on the fire around it, yes. But again, the reduction in temperature around the cars was significant. It was really good in mixing the hot gases and reducing the temperatures around and reducing the overall impact of the fire may have on the car park. Plus, it allowed for an access to the firefighters. So perhaps, yes, it could make spread in the direction of the flow worse, but I think it is multiple outweighed by the ability of firefighters to reach the fire, that's point one, and the significant decrease in the heat flux from your ceiling. This is the feedback loop we don't have, the heat flux from the ceiling to the vehicle. That's another student of mine and friend, Bojo Bogdanacenga, who will be doing his PhD on car fires, which will touch this particular feedback loop with the ceiling jets and vehicles that we hope to solve another interesting research project. So yeah, I hope this answers your question. Are we out of questions, Stash? We're out of questions. Thank you. So it was a huge pleasure to have you in here and share with you my first real scientific project that I've ever done with my team. Thank you to my team. Thank you to my support team, administration. You've been great and helped me achieve this. I hope we can get the financial part solved and get the audit passed, but I'm happy with it. It was a far path to get into where we are today, and I'm super happy I could share this with you. Of course, most of this will end up in academic papers, but you know how academic papers work. We first have to convince the reviewer that the location of the fire is not bullshit. So as soon as this is resolved, I'll be able to share with you those findings in a peer-reviewed form. And for now, that would be it. Thank you very much for joining us. See you around.